Picture 6 microservices, each one exposed directly to the internet. No shared authentication, no rate limiting, no centralized logging. A single vulnerability in one service, and an attacker has access to your entire system. No firewall, no token validation, nothing stopping lateral movement. This is what happens without a gateway. Now watch. A single intelligent layer appears between your clients and your services. Suddenly, every request is authenticated with JWT validation. Every call is rate limited using token bucket algorithms. Every response is logged with distributed traces. This is an API gateway, the single most important piece of your external API infrastructure. API gateways, the complete architecture. AWS API Gateway versus Kong Gateway. Here's what we'll cover. What an API gateway actually is, how a request flows through every layer, 5 architecture patterns for real deployments, deep dives into AWS and Kong, a head-to-head comparison with real metrics, and best practices from production systems. What is an API gateway? An API gateway is a policy-enforcing reverse proxy that sits between clients and backend services. Think of it as a bouncer, a translator, and a traffic cop, all in one. Clients on the left, your backend services on the right, and in the middle, the gateway. Every single request must pass through it. No exceptions. Inside the gateway, for core cross-cutting concerns, authentication, validating JWT tokens, API keys, or OAuth flows, rate limiting, protecting services from traffic spikes, request transformation, converting between protocols and formats, and observability, emitting metrics, logs, and distributed traces. Watch a request flow through. The client sends a request. It enters the gateway. The gateway processes it through each layer, authentication, rate limits, transformation. Then it routes the request to the correct backend. The response comes back through the same pipeline. That's the fundamental value proposition. One layer handles all cross-cutting concerns so your services don't have to. Now, a critical architectural distinction. API gateways handle north-south traffic. That's external clients communicating with your services. Service meshes handle east-west traffic. That's a service-to-service communication within your cluster. Both are needed. They're complementary, not competing. Here's the lineup. A load balancer distributes traffic at layer 4 or 7. A reverse proxy routes and filters at layer 7. An API gateway governs and protects APIs with policy enforcement. A service mesh handles service-to-service communication with mutual TLS. Key insight: gateways for north-south policy enforcement. Meshes for east-west communication. Both matter in modern architectures. Request lifecycle deep dive. Let's trace a single request through every gateway layer. 7 stages: TLS termination, authentication, rate limiting, transformation, routing, backend processing, and observability. A client sends an HTTPS request. Stage 1. TLS termination. The gateway terminates the TLS connection, validates the server certificate, and establishes a secure channel. Modern gateways use TLS 1.3, which eliminates the extra round trip of TLS 1.2 by combining the handshake. Stage 2. Authentication. The gateway extracts the JWT token from the authorization header. A JWT has 3 parts: header, payload, and signature, separated by dots. The header specifies the algorithm, RS-256 for RSA signatures, or HS-256 for HMAC. The payload contains claims, subject, issuer, expiration. The signature validates that the token hasn't been tampered with. If any part is invalid, wrong algorithm, expired token, bad signature, the request is rejected immediately. It never touches your backend. Stage 3. Rate limiting. The gateway checks a counter for this specific consumer. Most production gateways use the token bucket algorithm. Tokens are added at a fixed rate, and each request consumes 1 token. When the bucket is empty, requests are rejected. 48 tokens out of 50. Under the limit, the request passes. But what happens when the consumer exceeds their quota? The bucket is empty. 50 out of 50. The request is blocked with a 429 too many requests response. Your backend never sees it. This protects your services from both legitimate traffic spikes and denial of service attacks. Stage 4. Request transformation. The gateway rewrites headers, modifies the request body, and translates between protocols. Internal headers are stripped. Content type is converted, maybe XML to JSON. A unique request ID is injected for traceability. The client sees a clean, consistent API surface regardless of what your backends actually expect. Stage 5. Routing. Based on the URL path and HTTP method, the gateway matches the correct upstream service. Get/orders/123 routes to the orders service. Path-based routing is the most common, but gateways also support header-based, query parameter, and content type routing. The backend processes the request and returns a response. 200 OK. The response flows back through the pipeline. CORS headers are added for browser clients. Internal headers are stripped. gzip compression is applied to reduce bandwidth. Stage 7. Observability. The gateway emits 3 types of telemetry: metrics, latency percentiles, error rates, throughput per route; structured logs, consumer identity, route matched, response status; distributed traces, propagated trace IDs connecting the client request to every backend hop. In production, hundreds of requests flow through this pipeline every second. The same 7 stages, the same order, no exceptions. The complete request lifecycle: TLS, auth, rate limit, transform, route, and observe. Every request, every time. Architecture patterns. Pattern 1. The public edge gateway. The most common deployment. Client traffic enters through DNS resolution at Route 53, hits a CDN like CloudFront for edge caching, passes through a WAF for threat filtering, then reaches the API gateway, which authenticates, rate limits, and routes to backend services. This is the standard architecture for SaaS products and consumer-facing APIs. Pattern 2. Private internal APIs. Services within a VPC communicate through a private gateway. Zero internet exposure. Traffic stays internal via AWS private link or Kubernetes cluster IP services. This is essential for microservices that should never be reachable from outside your network. Compliance-heavy industries like banking and healthcare depend on this pattern for regulatory requirements. Pattern 3. Kubernetes ingress. The gateway acts as the ingress controller, or better yet, implements the new Gateway API specification. External traffic enters through a cloud load balancer, hits the Kong ingress controller, which uses Kubernetes native resources like HTTP route to pods. This is rapidly becoming the standard for platform engineering teams running microservices at scale. Pattern 4. The hybrid enterprise. Large organizations use multiple gateways. AWS API Gateway for serverless workloads and public APIs. Kong for Kubernetes and multi-cloud deployments. A service mesh like Istio or Linkerd for east-west traffic. Each gateway handles the traffic type it's architecturally best suited for. Central governance with decentralized operation. Each team manages their own gateway configuration. Pattern 5. Backend for frontend. Different clients, mobile, web, IoT, each get a dedicated BFF gateway that tailors the API surface for their specific needs. Mobile BFF returns compact JSON. Web BFF supports GraphQL. IoT BFF handles MQTT bridge. Each client gets exactly the data shape it needs, eliminating overfetching and underfetching. 5 patterns. Choose based on your topology, your team structure, and your operational maturity, not vendor marketing. AWS API Gateway. Fully managed. 0 servers to provision or patch. 3 API types. HTTP APIs. The modern choice at just $1 per million requests, with approximately 10 milliseconds of added latency. They support OIDC and JWT authorizers natively. REST APIs. The legacy option at $350 per million, but with richer features, usage plans, API keys, request validation, response caching, and AWS WAF integration. WebSocket APIs, real-time bidirectional communication for chat applications and live dashboards. The AWS integration ecosystem runs deep. Lambda for serverless compute, the most common backend. IAM for fine-grained service-to-service authorization. Cognito for user pool management and OAuth flows. CloudWatch for metrics and alarms. WAF for OWASP top 10 protection. VPC links to reach private resources inside your VPC. ACM for automatic TLS certificate management and rotation. Let me trace the full request flow through the AWS stack. Client sends a request. DNS resolved through Route 53. Edge caching and DDoS protection at CloudFront. WAF inspects for SQL injection, XSS, and custom rules. API Gateway authenticates via JWT or Lambda authorizer. applies throttling and routes. Lambda executes your function, 0 servers. Automatic scaling from 0 to thousands of concurrent executions. The response flows back. Lambda returns the result. API Gateway applies response transformations. CloudFront caches the response at the edge. The client receives the response. For private APIs, there's zero internet exposure. Clients within a VPC reach the gateway through a VPC endpoint powered by AWS Private Link. All traffic stays on the AWS backbone, never touches the public internet. HTTP API versus REST API. The key differences. HTTP APIs cost 70% less and have lower latency. But REST APIs offer API keys for consumer identification, built-in response caching, request body validation against JSON schemas, and usage plans for tiered rate limiting. Choose HTTP for new projects. REST when you need the extra features. The trade-off. Fully managed means zero operational burden, but you're locked into AWS. No multi-cloud portability. If you leave AWS, you rebuild your entire API layer. Kong Gateway. Open source. Built on Jinx and OpenResties Legit runtime. Runs on any cloud, any Kubernetes cluster, bare metal, anywhere. 3 deployment modes. Traditional, clustered Kong nodes all connecting to a shared PostgreSQL database. Simple, but the database becomes a single point of failure. Hybrid. The recommended mode separates control plane from data plane. DB-less, purely declarative YAML configuration, no database at all. Perfect for GitOps workflows. Hybrid mode in detail. This is the production-grade topology. The control plane stores configuration in PostgreSQL and exposes the admin API on port 8001. The data planes are the proxy nodes that handle actual API traffic. They connect to the control plane over a mutual TLS channel on port 8005. Configuration changes propagate automatically. Critically, each data plane caches its configuration locally. So even if the control plane goes down, your data planes keep serving traffic with the last known good config. The plugin chain is Kong's superpower. When a request enters, it passes through plugins in a defined execution order. Plugin 1, key authentication, validates the API key against Kong's credential store. Plugin 2, rate limiting, checks the token bucket counter, typically backed by Redis for distributed deployments. Plugin 3, request transformation, rewrites headers and body. Plugin 4, OpenTelemetry, emits distributed traces. Each plugin runs, validates, and passes the request to the next. Over 200 plugins available, and you can write custom plugins in Lua, Go, Python, or JavaScript. Kubernetes integration is native. Define routing rules using the standard Gateway API, HTTP per route, gRPC per route, TC per route, or use Kong's own CRD resources like Kong Plugin and Kong Ingress. Run kubectl apply, and Kong's controller watches for changes and auto-configures the data plane. The trade-off, maximum flexibility and portability, but you own the operational burden. You provision the infrastructure. You scale it. You patch it. You benchmark it. You monitor it. Freedom has a cost. AWS versus Kong, head-to-head. Operating model. AWS is fully managed. You configure, they operate. Kong is self-managed. You have full control, but full responsibility. Portability. AWS runs only on AWS. Kong runs on any cloud, any Kubernetes cluster, bare metal. Kubernetes. AWS connects via VPC links, an extra hop. Kong is the Ingress controller, native integration. Extensibility. AWS offers Lambda authorizers and VEL mapping templates. Kong has over 200 plugins plus custom plugin development. On latency, AWS HTTP APIs add roughly 10 to 15 milliseconds per request. Kong, running as a local ingress proxy, typically adds 1 to 3 milliseconds. On cost, AWS charges per million API calls. Kong's open source core means your only cost is the infrastructure you provision. Choose AWS when you're committed to the AWS ecosystem, running Lambda and ECS backends, and want zero infrastructure operations. IAM and Cognito handle Auth natively. CloudWatch gives you metrics and alarms out of the box. Choose Kong when you need multi-cloud portability, Kubernetes native integration, deep plugin extensibility, or control plane and data plane separation for global deployments. You also get full control over upgrade cycles and gateway behavior. But here's the real answer. The smartest enterprises don't choose one, they use both. AWS API Gateway for serverless public APIs where you want zero ops. Kong Gateway for Kubernetes workloads and platform APIs where you need portability. A service mesh like Istio or Linkerd for internal east-west traffic. That's the optimal architecture, each tool deployed where it's strongest. The organizations running the most reliable API platforms match each gateway to the specific traffic pattern it was designed for. Best practices and recap. 6 essential rules. 1. Configuration as code. Store all gateway config in Git. Deploy through CI/CD. Never click through a console for production changes. 2. Standardize authentication. Pick one pattern, JWT, Auth, or API keys, and enforce it organization-wide. 3. Per consumer rate limits. Global limits protect the gateway, but per consumer limits protect fairness. 4. Define timeout budgets. Set P99 latency targets per route and enforce them. 5. Benchmark plugin overhead. Every plugin adds latency. Measure the P99 impact before enabling in production. 6. Separate public and private API exposure. Never expose internal APIs through a public gateway. And the anti-patterns to avoid. Don't put business logic in the gateway. It's a policy layer, not an application server. Don't let each team build custom authentication. That's how you get 10 different auth patterns. Don't rely only on gateway rate limiting. Defense in depth means service level limits too. Don't expose admin APIs to the internet. The admin API is the keys to the kingdom. Don't force east-west traffic through the gateway. That's what service meshes are for. The golden rule. Use the gateway for cross-cutting concerns. Authentication, rate limiting, observability, routing, never for business logic. An API gateway is not a magic fix for bad service design. It's the policy enforcement layer that makes good service design work at scale. The complete mental model. Clients on the left, the gateway in the center, auth, rate limit, transform, route, observe, 5 layers, every request. Services on the right, AWS Gateway for serverless, Kong for Kubernetes, Mesh for east-west. Choose based on your topology, not vendor marketing. API Gateways, the complete architecture. Thank you for watching.